Hi everyone, Krishna this side. So in this video, we will cover this Hamiltonian path problem, but this time we will try to improve the time complexity. In the previous video, I have explained the code with the time complexity of having n factorial, which is in exponential, and we can further improve it. But when how we understand, right? So if we can apply bit masking or the problem falls in exponential, the constraint, if we look here, right? So if it is less than 20, then this type of problems falls into the exponential, or further if we want to improve it, we can use the DP with the bit masking concepts. Okay, so that's how we can analyze and get the idea, okay, this might be falling into that particular category or not. Okay, so that's the one thing. And yes, I'm not going to explain the same code again. So if you want to understand like how this problem has been solved so far, please make sure to watch the previous video. I'll just try to improve this code only, and will update how the time complexity got updated. Okay, and in this video you guys will get idea about some of the bit masking concepts as well, but I am not covering entire concepts here. The bit masking concepts I'll be covering in some other videos, but whatever the necessary bit masking concepts that are required for this video, I'll cover those topics. Okay, so yes, let's look into this notes that I have created here. So see, three concepts that we need to understand here. The first one is the left shift operator, and I just hope that you guys have idea like how a decimal number is been converted into the binary format. Okay, so it is pretty much simple. Let me explain that as well. So let us suppose if we have a decimal number 8. Okay, someone has created a int which is having value of 8. So in the binary format, how it is represented is uh, at the top, right? So I just denoted like how these values been created, and when we sum up, the sum should be equals to the decimal numbers value. Okay, so by default, from it starts with 2 to the power of 0, 2 to the power of 1, 2 to the power of 2 till to the power of n. If there will be eight, sorry, there will be n bits. Okay, that's how the representation happens. And see, if 8 is what the value we want to create, so 2 to the power of 3 is going to be 8, right? So the here if I consider that bit, so it will be 1, and rest all the bits will be 0. So how this happens is like 2 to the power of 3, that will be 8 obviously, plus 2 to the power of 0. If that bit is set, then the value should be 1. If it is not set, the value should be 0. So here if we look, right, so I have represented it the 8 in binary formation like this way. So 1, that will be 2 to the power of 3, and rest all the bit is 0, because we will add all the above values. Okay, 2 to the power of 3 plus 2 to the power of 2. So if that bit is set, what we will do is we simply multiply these values with the above value. Okay, so 2 to the power of 3 into 1 plus 2 to the power of 2 into 0, because I'm talking about 8. Okay, so 2 to the power of 2 into 0 plus 2 to the power of 1 into 0 plus 2 to the power of 0. So if we sum them up, we will get 8. That is the decimal formation that we are looking out for. For 4, this is how it represents. So 1, rest all the bits from there, in the left side will be 0, and in the right side they will be 1. So if we multiply them, all of them, this side it will be 0 plus 2 to the power of 2 plus 1, that will be 4, plus 2 to the power of 1 into 0, that will be 0, plus 2 to the power of 0 into 0, that will be 0 obviously. So ultimately that will give us 4. So if we want to represent further 3, so what we can do is rest all bits in the left side will be 0, it will be 1, and this one should also 1, because 2 to the power of 1 into 1 is 2, plus 2 to the power of 0, that will be 1, plus here it is 1, sorry, 2 to the power of 0 is 1, into here it should be 1. Okay, so if we sum them up, it will be 3. So that's how the binary representation happens for any decimal number. Okay, so I hope you guys get this idea now. And the first thing that we need to understand is the left shift operator here, because that will be getting used in this particular type of problems. So if any digit that we have, or any value we have, we want to left shift it by I times. So let us suppose I value is 2. What happens is, here 1 in binary representation is actually all these bits are 0, and it will be 1. So 2 to the power of 0 is 1, into 1, that will be obviously 1. So what we are doing is we have 0 0 0 0 and 1, that we are shifting the 0th bit, that is this bit, by 2 times. So what happens is this one will get shifted to here and two zeros will get added. So let us suppose if 3 is here, we have 3 here. So 3 is actually represented by 1 1 and all these bits are 0. Okay, so we are shifting by 2 times. That means only two zeros we need to add and rest all the bits get shifted there. So what happens is 1 1 by this side all them will be 0 and two zeros will be get added. So that is like it is going to be in a decimal format, it is 12, but our main focus is we are trying to shift two bits by left, we are shifting to left, we are using the left shift operator and we are trying to shift it by 2 times. So any value that we have, we are trying to shift it by any number of time value, whatever value we have here. So those many zeros will get added in the left side and rest all the bits will get shifted in the right side. Okay, sorry, left side. Sorry for that. So that's what a left shift operator basically does. Okay, so one left shift of 2 means two zeros get added and one that should be actually by default it should be at this place, right? So that gets shifted here and rest all the bits also get shifted in the left side. Okay, that's the first thing we need to know. Then there is like a set bit. If someone asks like yeah, this is the value I have and I want to set a bit in that particular value. Okay, so let us suppose 8 we have, that binary representation of 8 is 1000. So they ask to set ith bit. I is actually 2, so ith bit is this one. So it starts from 0th end SS. Okay, so 0 1 2. So they ask to set second bit, that is going to be this one. Okay, so second bit if they ask, so what we do is n or, so this is the or operator. Okay, so or and this is and these two operators also you guys needs to know. Okay, so there are few operators, those operators if I'll explain them in coming video. But what this or operator basically does is, if we are trying to do or operation between two digits. Okay, or there are multiple digits and we are keep on trying to do perform the or operation. So what happens is in or operation at any point, if we are performing or operation between these two, right? So 0 and 1, if at any point if there is one that set bit is there. Okay, that time automatically the answer will be set. Okay, what I'm trying to say is here it will be 0 and rest all the bits are 0, rest all bits are 0. Only when 0 0 is there, that time only 0 is what we get answer ultimately. Rest all the places whenever there is or and one, at only one set bit is also if there, then the answer is going to be set. So we have n is actually 8. So 8 is how, this is how 8 is been represented. That's what I already explained also. And one left shift of I means we shifted one by two times. I is actually 2, right? So this is how one left shift of I representation looks like. Then we have or operation. So 0 0 is ultimately 0, 0 0 is 0, 0 1 is going to be 1, and 1 here it is nothing but 0 only. So 1 0 is going to be 1 also. So that's how we set the bit. Okay, we use or operation to set any bit. If at all the bit is also set, then also 1 is going to be 1 ultimately. That's how the or bit works. Okay, or operator works. Okay, now if they ask like check if the bit is set or not. Okay, if they are asking us to like okay, check if I the bit I is actually 2 again, if that is set or not. So what we can do is, instead of here or, we will use and operator. So what and operator does is like both the bits should be 1. Okay, no matter let us suppose if we are trying to perform AND operation between 3 digits, so all the 3 digits should be 1. Okay, that's the or AND operator's motive. Because if at any point in time if we get 0 or 0 0 0, doesn't matter. If at any point in time if there is the bit is not set, the ultimate AND operation is going to be 0 only. Okay, so let us suppose n is actually this. Okay, now I am using 12. So 12 is how, this how 12 is represented, and they are asking check I the bit is set or not, that is I is having 2. So n and one left shift of I. So one left shift of I already explained. So this is how it represented, and the 12 is actually this is how it represented. And if we perform and, as I said, 0 0 is 0, 0 0 is 0, 1 1. So both are 1, both the bits are set. Okay, then only 1 will we get. Okay, and here 1 0 is ultimately going to be 0. Okay, so doesn't matter. So in and, if at any point in time if we get one set bit also, then also the answer, in the answer that bit is going to be set. But in and both the bits, if only if both the bits are set, then only we will set the answers bit. Okay, so this answer is going to be 4 at any point in time. If we are even checking the zeroth bit, okay, here if it is 1, they are asking I is actually equals to 0, and they are asking check if zeroth bit is set or not. And here supposingly if it is 1, okay, the bit value is actually 13. So if it is 1 and we perform I one left shift of 0, that is going to be 0 0 0 1. So both are 1, then this is 1. So ultimately that is going to be greater than 0. So if at any point in time if this value we are getting, because this is going to be obviously greater than 0, right? And nothing, if there is nothing at all, then also this value is going to be 1 at if the bit is set. So if that is greater than 0, that means the entire the bit is actually been set. Okay, because we are checking only that particular bit only, rest all of them are 0. And in AND operation, if at any point in time if only single 0 is also there, that bit is not set, then the answer is going to be not set in that condition only. Okay, so if they asked first bit is set or not, so I left shift of 1, so it is like 0 0 0 1 0, and we check here it is 0 and here it is 1. So ultimately it is going to be 0. This bit is also 0 for now, with the as in we are checking for first bit. So this is also 0 0. So rest all are 0. That means like it is not greater than 0, right? So we are getting 0 only. So the bit is not set in that case. That's how we can check the bit if it is set or not. Okay, so these three concepts we are required here to solve this type of problems. Okay, now what is how we approach to this one, right? So what we can do is we will create a DP array, and each of the vertex that we have, we represent it as a bit, because n is actually less than or equals to 10. That's what the constraint says, right? So we can easily accommodate the bit masking with this type of problems. So each bit that we have, we represent it as a set bit or not. Okay, so we have only 4 nodes here. So what we can do is this will represent, so zeroth bit will be represent the zeroth node, first will represent the first bit, second represents the second bit, third represent the third bit. And all these bits, if they are set, that means all of these values are 1 1 1. That means we somehow travels all of these nodes. Okay, so at any point in time if we reach that node, we what we do is we always try to set that bit. Okay, so see, now in the previous video, if you remember, we tried all the possibilities, right? So from 0 we tried explore all the possibilities if we are able to get the answer. From 1 we tried exploring all the possibilities if we able to get the answer. So same thing we do, but this time we use that n. So we used visited array, right, previously. So visited array, here with the visited array what we will do is we will be having all the possibilities that we can have, right? So one left shift of n, that is like one left shift of, here n is actually 4, right? So one left shift of 4 means it is going to be represented as 16. 16, so n is like 4 into 16. So this is the DP array size we have. Okay, that's how it basically gets represented. Okay, DP array, so from 0 to till 15. So one left shift of 16. So see, 16, why I'm saying 16 means, like, if let us suppose we started exploring from 1. Okay, and we what we will do is each time when we visit that particular one, what we will do is we will create a mask. Okay, so what is basically mask means, so one left shift of n, that is like one left shift of 4 is like 16. 16 means like uh, all the 4 bits actually get set or not. For that we will use this mask, and ultimately if all these bits are set, that will be represented as 1 1 1 1. Okay, that value is actually eventually going to be 15. So what we will do is, so mask, whatever the mask we have, minus 1 should be equals to all this set bit. Okay, so ultimately if at any point in time if we visited all of these bits, what we will do is the mask value is going to be 15, and we compare with the current mask that we have, because that's the n value we have, right? So 4 times. So if both the values are matching, 15 equals 15, then that means like we explore all these nodes, right? So at any point in time if we visited that node, we will simply set that particular bit. Okay, at zeroth node if we are currently so what we will do is our mask will be zeroth bit, we will set that. When we explore to 2, the second bit that we have in the current mask is 0 0 0 1. And what we will do is now we check that if the second bit is set or not. If it is not set, that means we haven't explored that one. So what we will do is we simply set that second bit, and new mask is going to be 0 1 0 1. Okay, now from 2 we can go to 3, or even we can go to 2, but what here now, instead of visited array, with the help of mask only we check if the bit is set or not, because from 0 we reach to 2, right? So again, if we want to go back to 0, 0 is already visited, right? That means the mask, in the mask, the 0th bit is already set, right? So what we will do is, we now, instead of visited array, we will check with the help of the mask, that current mask that we are following. We check that if the bit is actually set or not. So 0th bit is already set, so we are not exploring to the 0 for this 2, as in considering the addition node. We will check for the 3. Now the third bit is not actually set, right? So 0 1 0 1, that is the mask we have. So what we will do is, we simply update the mask. So we set that bit, and how to set the bit I have already explained you. We will use OR, and we shift to this one left shift to 3, and we perform the n is actually the mask, current mask that we have, and we set that bit. So simply that is like 1 1 0 1. Okay, from 0, as I started going downside, we visited all these nodes. Now from 3 we are not going anywhere. So ultimately, the mask, current mask, is actually not equals to the mask value that we are checking for, because if all the bits are visited, then the value should be 15, right? So we are not, this current value what we got is not actually equals to 15, and there are no further possibilities also, right? So yes, of course, now here, from here, we are not getting any further possibilities, so we simply return false, and we keep on filling this DP array with the false value, because at any point in time, let us suppose from 0, again, if I revisited the same node. DP is how, like, memorization, that's how things works, right? If the DP array is having the, if we explored that particular path previously, then why we want to explore, revisit and re-explore that particular path, right? That's why we are using the DP here, right? So with the help of this, like, from 0 we tried exploring all the paths, and we are storing those values. If whether the value is true or false, doesn't matter. So whatever the value we are getting, we are keep on filling into this DP array, so that at any point in time, if we are trying to explore from 1, and the mask value is, let us suppose 7, the DP, if the DP array is having that value, definitely we are not revisiting that, right? We are not recomputing that. So we simply avoided the further exponential thing that is keep on happening, right, with the help of DP array. So yes, I know some of you guys might not have still understood few of the concepts, but if once I start writing the code, and again we come back here, and I'll explain you, you guys might get the idea. Okay, so see, if all the vertices we visited, then our current mask will look like this. Okay, so as in, we are keep on setting the bit, right? So all these value actually represented as 15. So see, like, as I already explained you, like, starting with 0, if we explode from 0 we reach to 2, from 2 we reach to 3. Okay, so our mask should be like this. We set all these type of bits. Okay, 3 is actually we are setting this bit, whatever the current mask that we have, we ultimately set that bit for that one. 2, for 2 we already set this, and for 0 this. We compare this with the current mask value, because one left shift of n minus 1 is actually 16 minus 1, that is 15. So this, all the bits, if they are set, value should be 15, and that is what, like, we will compare it ultimately. So that's our base condition is going to be. If the base condition is matching, that means, like, from a particular node we could able to visit all the nodes exactly once, right? So that means we simply return true from there, and ultimately the answer is going to be true. Okay, so see, I'll again explain the same concept. Okay, so let's start from the 0th node, and the current mask is actually one left shift of I. So I is actually 0. Okay, all these node values are basically what I am considering that it is I. So the current mask is actually 1. One left shift of 0, that is 1. Okay, so that is like 0 0 0 1. Now explore adjacent nodes to 0. So what is the adjacent node for 0? 1 is there and 2 is also there. So let us suppose we explode from this side, and check if the first bit is set or not now in the current mask. So the current mask is 0 0 0 1. So we check if the bit is set or not. So the first bit is set or not ultimately, right? Because we are representing these values with the mask only, right? So we check that it is not set, right? So 0 0 0 1 is what we have. So what we will do is, we will set that bit. The mask is now one left shift of 1, that is like 0 0 1 is what we have currently. And okay, 0 0 1 is what we have, and the next value when we do one left shift of I, that is 1, because we are at now 1. So that is going to be 0 1 0, and we will perform our operation with 0 0 1, that is like 0 1 1. That's what we got. Okay, now we will start exploring when we reach to 1 with the recursive way. We'll start exploring from 1. So from 1 we have addition node as 0, but now here instead of visited array we have the currently mask right with us. In the mask we can easily identify that whether the value is set or not. Okay, so we will check that in the mask if the value is actually set or not, the bit is set or not. So same here I have shown you, right? So current mask is like one left shift of 1, that is like 110, and we are actually checking the 0th bit is set or not. Okay, so 0 0 and 1. Okay, so when we perform this and perform the AND operation, because we are checking whether it is set or not, so this ultimately should okay, I don't know like what I have written here. We should I just ignore this part. Okay, so we want to just check that whether the 0th bit is set or not. The current mask is what we have, 0 1 1, and from 1 from 0 we reach to 1. Now from 1 we have only 1 node to 0, right? So the current mask is 0 1 1, and to check whether the 0th bit is set or not, we simply perform AND operation, and what we will do is one left shift of 0, that is ultimately going to be 1. So the current mask is 0 1 1, and the new mask is like 0 0 1, and if we perform AND operation, the value what we are getting is like 0 0 1, which is greater than 0. Okay, so the value is actually greater than 0, right? So that means that bit is already set. So from 1 we are not going to revisit again 0, right? Because from there only we actually came here and the mask values got updated. So we simply return false from here, and DP values also get updated with that particular mask value. So that's how we keep on filling these values. Okay, from the 0th node we explore all the possibilities, and from 1 also we try to explore all the possibilities, and the bit this mask is something what keep on getting these values, and DP table is being filled. And at any point in time, if we try to revisit the same nodes which we previously already explored, okay, in the exponential graph, then we simply avoid that and we return the DP value. Okay, let me write the code, and again I'll try to explain you. So I'm not going to write this new code. I'll just try to improve the code. Okay, so instead of visited array, now what we have is, let me create a non-primitive data type. Okay, Boolean DP. We can use int and all also, but that needs to be get filled again with -1 and all. We'll just wanted to avoid those things. So what I'll do is I created a non-primitive data type, because by default it will be having null value. With primitive data type, it is going to be filled with false, right? And I don't want to have that condition. So Boolean and one left shift of n, because all those operations should be there. Okay, so now what we will do is we again start from the 0 till n node we will be reaching, but instead of visited we have DP array here. The total is actually what we have n, that is fine. So the n instead of n, it will be like the mask value. Okay, what is that mask value? One left shift of n. Okay, that is what the total we want to check with. Even here only we can update it, one left shift of n minus 1. And now this value basically represents uh, 15. Okay, that means all the bits are set. We just want to make sure that we will be comparing it, and let me create the mask here outside only. In mask equals one left shift of n. Let me put this at the top, because in the boolean here also I'll update it. Okay, instead of writing here that, I'll keep mask here, and mask -1 is what I want to pass. And here the first bit is set, the ith bit is actually set now, right? So this is our current mask, and we will be checking with this mask. Okay, ultimate goal is we want to reach to this mask. So now these values, let me update is that these values as well. The current is same. Instead of visited we have boolean DP, and instead of total, let me write it as mask, and this will be current mask. Okay. So the visited thing is not going to be there now, because we are checking with the mask thing, if in the mask if that bit is set or not while exploring all the path. And now instead of total, we will check if mask equals current mask, because we are keep on we will be keep on updating the current mask. So we return true ultimately. Now since we are using the DP, so we will check whether the DP of current current and one left shift of current. Okay, that's what we are trying to do, is right. So one left shift of current. Sorry, this is like another blunder I was doing here. So the mask is what we have, right? So if it is not null, if this value is not null, the current mask value is not null, then we simply return the DP of current and current mask, whatever it may be. If it is having false value, true value, okay. Since it is non-primitive data type, it will be by default null, but at any point in time if we got some values, whether it is true or false, that is what I want to return ultimately. Now we will loop again the same. We will check adjacent nodes, and instead of visited here, we will be having the condition for the mask, whether the bit is set or not in the mask, right? So in the current mask, what we will do is we will perform AND operation, one left shift of ADJ node. This node current, the addition node, or let us name it as a next. Next, let me update everywhere. Next, so the next bit that we have, whether it is set in the current mask or not. If this value one left shift, and if this is giving us, okay, let me add the brackets. If this value is equals 0, that means the bit is not set, right? So ultimately we want to enter into this if condition. So if DFS of this next adjacent, now here it will be, instead of visited, it will be DP. The mask is going to be same, but the updated mask is like we want to set that bit, right? So current mask, or we are setting the this particular next bit, okay. So this is like we are updating that bit. So the current mask is now, let's suppose if we are at 0, the current mask is like from here it is like 0 0 1, and we explored the artisan node as 1. So the updated mask is like the in the current mask it is not set, right? Obviously the first bit is not set, so we are just setting the bit. Okay, so we will keep on doing this operation until all the bits, actually with the current mask all the bits are actually set, that is like 1 1 1 1. So ultimately if that is the state, then we simply return DP of current and the current mask is equals to true. Okay, so that's what we want to return here. We will remove this part of code, and at the end, if it is not, then the in the current, in this DP of current and current mask we will return simply false. We'll fill that. Okay, that's it. Like that's how we update the code. Let me try to run it if we have any mistakes done. Let me check that. Okay, it is running fine. Let me submit it as well. Okay, it is working fine, right? So yeah. So now see what is the now time complexity, right? So time complexity is right here. This may run constant, or in a worst case this may run n into this mask, that is 2 to the power of n, right? And we are again running this for loop also. But by default, like in the most of the standard ways, we consider this as a constant time only. So this n is what we are exploring. So n into this will be like 2 to the power of n times, because one left shift of n is like 2 to the power of n only, right? Ultimately, so that many times we are checking, right? So n 2 to the power of n is what the time complexity is going to be, and the space is actually the same, because we are maintaining the same boolean array. So we reduced from the exponential to 1 n into 2 to the power of n. So that's the new complexity, time complexity we have, and the space is also I have updated. So I guess you guys got some idea. If not, I mean, I'll keep on bringing this DP with bit masking concept topics in the coming time, and I'll try to explain more clearly. Okay, if you guys still didn't get from this video. Okay, so that's all from this video, and I hope you guys got some learning. So yeah, bye bye.